Hello students, welcome to the class on control engineering. So in this video we are going to solve another variety of problem on Bode plot. So g of s into h of s has been given. So this is a given g of s into h of s. So for this we need to find out the Bode plot and comment on the stability. So what is the difference between the previous problem and this problems? Here you can see one of the quadratic pole is been given. So you need to verify first whether this is a quadratic pole or not. Sometimes to confuse the students, they are going to give like this. So you need to verify whether the given equation is a quadratic or not, that is a complex roots or not. So how to verify that? We need to verify by applying this formula minus b plus or minus square root of b square minus 4ac divided by 2a. So if we find out this is a complex pole or a complex zero, then only we need to apply the required procedure. I hope you understood. So I have applied minus b plus or minus b square minus 4ac divided by 2a, and I found out that this is a complex. So therefore I am going to explain the steps. Okay, so what is step number 1? So as we all know that step number 1 is to convert the given standard forms to time constant form. So let us do it. So step number 1, so I am going to convert this g of s into h of s. So 242, so I am going to take 5 as common, 5 in bracket 1 plus 5 by s by 5, right? S by 5. Next, yes. So here if I take 1 also no change, 1 plus yes. So here I am going to take 121 as common, 121. So then this can be written as 1 plus 5s divided by 121 plus s square by 121. Okay. So next, if I simplify this, so I got 10 into 1 plus s by 5 divided by s 1 plus s into 1 plus 0.041 s plus s square by 121. So this is a g of s into h of s. So in the time constant form. Okay, so this is standard form. So I have converted this into a time constant form. Next, step number 2. What is the step number 2? We need to find out identify the factors. Okay, so let me do it in a fresh sheet. So step number 2 is to identify the factors. Okay, step number 2, identify factors. So what are the various factors are there? So in this, what is the value of k? So from this we found out that first factor, that is k, is equal to how much? 10. Okay, so second factor, what is second factor? How many poles at the origin, whether poles or zeros at the origin. In this problem we have one pole at the origin, therefore the second factor is one pole, that is 1 by s at the origin. This is the second factor. Next, third factor, I have a simple pole, right? So one simple pole, how much is that? 1 by 1 plus s. So we need to find out the corner frequency, omega c is equal to omega t. So in this case, what is t? It is 1. So therefore it is 1 radians per second. Omega c is equal to 1 radians per second. Next, fourth factor. What is the fourth factor? So I have a simple 0. Simple 0. What is a simple 0? 1 plus s by 5. See, 1 plus s by 5. So what is the omega c? 1 by t. Here what is t? It is 1 by 5. Therefore it is 5 radians per second. Next, fifth factor. What is the fifth factor I have? I have a complex pole, right? So when I have a complex pole, what to do? So I have a complex pole, that is, so I am going to take this standard form, that is 1 by s square plus 5s plus 121. Why? Because I need to find out the corner frequency. How to find out the corner frequency? For this, I am going to compare this with the standard quadratic form. What is standard quadratic form? 1 by s square plus 2 zeta omega n s plus omega n square. So this is a standard quadratic form. So I am going to compare these two. I found out that omega n square is equal to how much? 121. That means omega n is equal to how much? 11. Okay, omega n is equal to 11. So what is the value of zeta from this? So 2 zeta omega n is equal to 5. Therefore zeta I got is 0.22. Okay, so here omega n is nothing but what? Omega c. Okay, so that itself we are going to take it as corner frequency. Now after finding out the corner frequency, that I got 1 radians, 5 radians, and also I got 11 radians per second. Okay, so out of these three, which is the lowest? So that's the 1. So this is the corner frequency 1. So next greater number, that is 5 radians, that is the omega c2. Next this is the omega c3. So these are the corner frequencies. Okay, what is the step number 3? Step number 3, after finding out the various factors, step number 3 is to draw the magnitude plot. Okay, magnitude plot. So how to draw the magnitude plot? So for this, so we are going to consider the first factor, that is a k. We are going to identify the contribution of k. Okay, first factor, what is the k is equal to how much? K is equal to 10. Therefore magnitude 20 log k, that is 10 to the base 10. So how much is this? That is equal to 20 dB. I got it, 20 dB. Okay, so now what to do with this? So since k is greater than 1, I am going to draw a parallel line above the 0 dB line. So draw a parallel line above 0 dB at 20 dB. Okay, so let me show you how to do it with the in the semi-logarithmic sheet. See, I am already ready with the preparation. I have already marked the 0 dB. Slope of 20 plus 20, this is I marked 20 dB plus 20 plus 40 plus 60, 80 and minus 20. After that I have drawn a slope. So this is slope of minus 20, minus 40, minus 60 and minus 80. So in the same way I have prepared for the phase angle plot also. Okay, so what are the initial preparations I have done? It is done. So now what? So first I need to identify the corner frequencies. What is the corner frequency 1? So that is 1 omega 1, that is 1 radians per second. So and I am going to draw a line above. So this is the corner frequency 1 omega c1, that is 1 radians per second. What is the corner frequency 2? So omega c1, let me mark with the sketch pen so it will be easily visible for everyone. Next, omega c2 is how much? So it is 5 radians per second. So 1, 2, this is 2, 3, 4 and 5. 2, 3, 4, 5. This is a 5. Right? So this is a omega C2, that is 5 radians per second. Next, what is omega C3, that is 11 radians per second. So this is 10, so this is 20, and this one is 11. Okay, this is 11 radians per second. I am going to mark it like this. So this is omega C3 is 11. So omega C1 is 1. Omega C2 is equal to 2. And we should know, so this is a simple pole. 1 radians per second is due to the simple pole. Omega C2, it is due to the simple 0. This is 0, and this is due to the complex or quadratic pole. So this is very much important. Okay, so omega C1 is due to pole, omega C2 is due to 0, and omega C3 is due to pole. This is very much important. You need to mark it. So after this preparations, what we have to do, first we need to draw the magnitude. How much is the magnitude? We found out. Where is the magnitude? Okay, wait a second. Okay, so magnitude is equal to 20 dB. So from the 20 dB line, 20 dB, I am going to draw a line parallel to the 0 dB above this, right? So this is the magnitude or contribution of K. Okay, so this is the contribution of K, that is 20 dB. I hope you got it. Okay, after drawing the 0 dB line, what is the next step? So from the 1 radians per second, that is a reference, usually we did all the previous problem. From 0 dB, I am going to draw a line, vertical line upwards until it touches the magnitude line. Okay, so after drawing this point, so next step is to next factor, right? So what is the contribution of factor number 2? Which is second factor? So I have one pole at the origin. Okay, so one pole at the origin contributes how much? Contributes minus 20 dB per decade, right? See, one pole at the origin contributes how much? Minus 20 dB per decade. So how to draw this? So from here, I am going to draw a line from this point, okay, so which is parallel to slope of minus 20. Okay, I hope you got it. I am going to draw the slope of minus 40 from this point, and I need to extend up to the corner frequency 1 and make a note here. Here omega C1 is equal to 1 radians per second. So therefore this will be the line up to the corner frequency 1. Okay, so this line is due to the contribution of K and one pole at the origin, that is 1 by S. Okay, so at omega C1 1 radians per second, what is this? This is a pole, right? So we have a one simple pole. So therefore what is the contribution of that third factor? At omega C1 is equal to 1, we come across what? One simple pole. So what is the contribution of this? So simple pole contributes how much? Minus 20 dB per decade. So simple pole contributes minus 20 dB per decade. Okay, so resultant slope, what is the resultant slope? Previous slope was minus 20, so contribution of this is minus 20, so therefore resultant slope is minus 40 dB per decade. Okay, what to do next? So from this corner frequency 1, I am going to draw a line of slope minus 40. Okay, so minus 40 until it touches the corner frequency number 2. Okay, until the corner frequency number 2. See, this is a line is due to k 1 by s and 1 by, what is the, wait a second, there is a problem, right? So 1 plus s. Okay, so at omega c2, that is a corner frequency 2. What is this? This is due to the simple 0. So we come across a simple 0. Fourth factor. What is the fourth factor? At omega c2, that is 2 radians, sorry, 5 radians. Yes, 5 radians per second. 5 radians per second. We come across 5 radians. Come across simple 0. Very much important. We come across what? Simple 0. So what is the contribution of simple 0? It is plus 20 dB. So therefore, what is the resultant is, previous slope is minus 40, contribution of simple 0 is plus 20. Therefore, the resultant is minus 20 dB per decade. Okay, what to do then? In this magnitude plot, from this point, I am going to draw a slope of how much? Minus 20, like this. Okay, so this is a contribution of what? K 1 by s and 1 by 1 plus s and simple 0 1 plus s by 5. Okay, so at this point it is going to come across a quadratic pole omega c3, right? Quadratic pole at 11 radians per second. At omega c3, that is 11 radians per second, we come across quadratic pole. So let us see what is the contribution of quadratic poles. Okay, simple pole is what? Yeah, here we got. So at quadratic pole, the quadratic poles are going to contribute minus 20 dB per decade. It is going to contribute minus 20 dB per decade. Okay, therefore what is the resultant slope? Previous slope was minus 20, contribution of this quadratic pole is minus 40, therefore it is minus 60 dB per decade. Okay, so I am going to draw a line from this point of slope of how much? It must be a slope of 60. So slope of 60 I need to draw. This is a contribution of k 1 by s, 1 by 1 plus s, 0 1 plus s by 5 and a quadratic pole. So this is a final contribution. Okay, so this is how we are going to draw the magnitude plot. See, one variation is there. What is that? Whenever we found out the quadratic pole or a 0, we need to apply the correction factor. So what is the correction factor for a poles? It is minus 20 log 2 zeta. Okay, minus 20 log 2 zeta. If it is a 0, it will be plus 20 log 2 zeta. So this is a corrective factor that we need to apply. Okay, what is the corrective factor we got? So let us see corrective factor. Corrective factor that is equal to minus 20 log 2 zeta. Minus 20 log 2 zeta. So what is zeta? So previously we calculated the zeta, right? Okay, so we already calculated the zeta, that is 0.22. Okay, if I apply here minus 20 log 2 into 0.22 2 zeta. So therefore we got it is plus 71.13 dB. 7.13 dB. So how to apply this corrective factor? Let me explain you. Okay, how to apply the corrective factor? We found out that it is plus 7.13. Okay, see here, if it is positive, correction upwards. If the corrective factor is negative, correction downwards. So now we got plus 7.13 dB. So therefore the corrective factor must be above. See, from this point where omega C3 is 11, so each unit represents what? 4 dB. So I need to have a corrective factor of how much? 7.13, approximately 2 units above 1 and 2. Okay, this is the corrective factor I marked. So here I am going to draw another line like this, a arc like this. Right, so this is the corrective factor. From this point to this, it is how much? Plus 7.13 dB. So this is how we are going to mark the corrective factor. I hope you understood. So next step, so this completes the drawing the magnitude plot. What is the next step? Next step is to draw the phase angle plot. Okay. Step number 4, phase angle plot. For this, what we need to do? We need to construct the table, right? So we have to construct the table. So here we are going to vary the value of omega, right? So next, we have totally 5 factors are there. The first factor is k, and we have one simple pole I omega. Next we have, so I will write it here. So we have a time constant form, that is the time constant form. Yeah, so we have time constant form 10 1 by, wherever s is there, I am going to write I omega divided by 5, then I omega 1 plus I omega or j omega, no problem, 1 plus 0.04 I omega here, so plus I omega square divided by 121, correct? So this is the, we got it. See, after simplification, so this term will be 1 plus 0. 0. Right, so this can be simplified. We know that I square is equal to minus 1. So we are going to apply this. We found out. So this term, so I am talking about this term. Thus this can be written as 1 plus 0.041 I omega. So there I square, that is I square term, right? So this is I square. So this can be minus omega square divided by 121. Okay, so these are the 5 factors we need to construct a table. Okay, so let me draw the table here. So we are going to vary the value of omega. Then k, the first factor is k. The second is one simple pole j omega or I omega. Next we have a simple pole, that is, can write it as minus tan inverse of omega. Next we have a simple 0, so this can be written as plus tan inverse of omega by 5. Okay, next this is a quadratic pole, so therefore this will be minus tan inverse of y. What is the value of y? It will be what is y? So 0.041, right? I omega, sorry, not I, so only omega, so divided by 1 minus of omega square by 121, and the final corner will be our resultant, right? So we have to form the table like this. We have to form the table. Okay, now for the various values of omega, so I am going to vary the value of omega by 0.2 to 10, 50 and 100. So I am going to vary these 5 values. As we all know, what are the contributions of this, right? What are the contributions for phase angle part? So first factor, that is k is greater than 0. So here k value is equal to 10. So what is the contribution of this? It will be 0 degree. For all values of omega, it will be 0, 0, 0, 0. Next, we have a simple pole. What is the contribution of one pole at the origin? It is minus 90. So we have one simple pole, contribution is minus 90, minus 90, minus 90, minus 90 and minus 90. Next, we need to calculate these 3 factors when omega is equal to 0.2. So this is 11.30 minus 63.43 minus 84.28 and minus 88.85, and this is minus 89.42 for the values of omega 0.2, 2, 10, 50 and 100. In the same way for this, so this will be 2.29, so 21.80, 63.43, 84.28, next 87.13. Next, this is the value, so this will be 0.469, this is minus 4.84, this is minus 67.05, so this is plus 5.95, this is plus 2.87, right? So this is the values of this term. So when omega is varied from 0.2 to 100. So now what is the resultant of this from k to this? So I am going to summation of all these 5 factors. This will be equal to minus 99.47. So this value is minus 198.68. This one is minus 177.9. This one is 88.62 and this one is minus 65.63. Okay, so these are the resultant. Okay, so now we have to represent this in the plot. Okay, let us take this plot. So now I need to draw the phase angle plot. Okay, at 0.2, so this is 0.1, this is 0.2. What is the resultant slope? It is minus 99.47. So somewhere here nearby, this is a 99 0.47 approximately. I am doing it. Next, at 2 is what is the resultant slope? It is minus 198.68. 198.68 at the value of 2, right? So this is a 2, 198.68. so it is between minus 180 and 210. This is 180, so each unit will be 6, right? 6, 186, 192, 192. I need to represent 192. This is a 198, so approximately this value. Okay, so next one, when it is 10, okay, when it is 10, so it is minus 177.9. when it is 10, so it is equal to 177, right? So 177, this is 110, this is a 190. Second, okay, almost nearer to the 170, right? Sorry, 177.9. wait a second. Okay, at 10, so it is 177.9. so this is 180 minus 180, 1 minus 6, it will be 174, somewhere here. Okay, this is 177. okay, next, when it is 50, so it is minus 88.62. when it is 50, this is a 10. Okay, 10, so this is 10, 20, 30, 40, 50. when it is 50, it is 88.62, somewhere here. 98.62, somewhere here it will come. Okay, so like this we are going to join approximately. So now I am going to draw the graph. So connecting the various points with a smooth curve, so from here to here, then it will gradually goes like this, So this is a phase angle plot. Okay, what next? So now we need to find out the omega GC and omega PC for this. Okay, now how to calculate omega GC? See where this magnitude plot crossing the 0 dB line. So this is the point where it is crossing. I am going to draw a vertical line downwards. So this is the omega GC. I am going to extend the same. So this is the omega GC, that is the gain crossover frequency. What is that frequency? Is 1, 2, 3. So it is between 2 and 3. So plus 3, 2.1, 2. So approximately it is 2.7 radians per second. Omega GC is equal to 2.7 radians per second. Now I need to calculate the omega PC. So here it is crossing this point. So where the phase angle plot is going to cross the minus 180 degree. So this is the phase angle plot. Omega PC. Okay. I am going to extend this. This is the omega PC. This one is omega PZ. How much is this? This is 1. This is in between 1 and 2. So it is omega PC is equal to 1.5. See here, omega GC is equal to 2.7 radians per second. Omega PC is equal to 1.5 radians per second. So now what is the comment on stability? Pay attention here. The second condition, when omega GC is greater than omega PC, GM and PM will be negative, so that you can verify it, right? So where is the omega PC? So this is the omega PC phase, omega PC. So we're going to move it upwards. It is going to intersect the magnitude plot at A, right, as well as at the 0 dB line. Okay, so this is a B. So this is above, so therefore it will be negative, right? So it will be negative. So take the measurement, how much box? So 1 to 2.2. So approximately this is the gain margin. Gain margin is equal to 12. Approximately it is 12 dB. Gain margin is how much? 12 dB. Now I need to find out the phase margin. For that we need to consider omega GC. Extend the line downwards. So it is going to intersect at minus 180 at C and also this phase angle at D. So measure this units. How many units you got? 1, 2, 3. Approximately 3 units. Each unit represent 6 units, 6 degrees. So therefore phase margin, so this will be in terms of negative, will be minus 6, 12, 18, minus 18 degree. Okay, so gain margin at omega PC is minus 12 dB and PM, that is a phase margin at omega GC, is minus 18 degree. Okay, minus 18 degree. Therefore GM is equal to how much? Minus 12 dB. Phase margin is equal to how much? Minus 18 degree. So what is the comment on the stability? Since, what is this? Omega GC is greater than omega PC, GM and PM are negative, the system is unstable. System is unstable. So this is the main comment that you have to write. I hope you understood. Thank you. Namaste.